Okay, let's get started, everyone. So welcome. Um, just doing one more check. Can everyone hear me? Excellent. Okay. So first thing we should do is just. God, I wish this worked a little more seamlessly. So for today's. Wait, where is this? There we go. All right. So for today's little bit of humanity to introduce into here, we are. I invite you all to look at this babbling brook. I actually photographed this myself while I was on one of my famous nature walks. As I pointed out, one of the only things that you're allowed to do these days. But the thing that's interesting about this is I was doing this while I was walking to the pole farm. I'll explain that in just a second. Let's see. Where do we go? God, I wish this worked more seamlessly than this. That. No. Stop sharing. Oh, wait. Okay. That. Share your screen. There we go. Okay. So, as I had mentioned, one of the places one of the interesting places that you can walk near my house is this thing called the pole farm. If you look at the left part of the screen, what you'll see are just a bunch of what look like high voltage transmission lines. But actually, this is a picture that was taken in roughly the 1920s. There was a time that before they could lay undersea cables for international phone calls, there was someone had figured out that shortwave radio was just the right frequency to be able to beam a signal all the way to Europe. Because AT&T has always been headquartered in New Jersey, and they were the company that ran this. It's actually right in our backyard that all international calls from the United States took place. They would use landlines to deliver calls to central New Jersey, where they would be beamed across the oceans. The technology was so clumsy that the only way to do this was you actually had to put the transmitter and the receiver 45 miles apart so that they didn't interfere with each other. AT&T's headquarters was roughly in the Middletown, New Jersey area, so they put their receiver in Middletown, but they needed a location about 45 miles away to put the transmitter. And they put it just outside of Princeton, New Jersey. And these big poles that you see on the left, which are roughly 350 feet high, nearly as high as about 2/3 of the way up the Statue of Liberty, they were just sitting out in what's now just a big farm. This was the early technology, and eventually they switched to this technology that you see right here, which were much shorter wooden poles that held diamond-shaped antennas called rhomboid antennas that were aimed at various different cities. The larger poles you see they were like a mile-long array that was exactly pointed at the city of London. When they switched to these smaller ones, they could reach a lot more cities. So there's a park now that's dedicated to this history, and there is one pole standing. You can see this is the one pole that's standing. This is the remaining pole from rhomboid antennas. And according to the plaque next to it, it says that this was part of a group of four forming a diamond that was pointed at Tel Aviv. So that's today's history lesson. Hope that was a nice interlude before we get to the actual math. So maybe on Monday we'll return to poetry. We'll try to do something like this. We'll try to do something like this basically every day. Okay. So let's get back to. So I've got to the laptop. So I can do this. Yeah. So if you recall, anyway, if you recall what we were doing at the very end of class, we were covering the theorem called Rolle's theorem. I apologize, I just want to turn off the camera so you don't need to see me, you just need to hear me, and you need to see the slides. There we go. Okay, so we're covering a theorem called Rolle's theorem, or Rolle's lemma, and essentially what Rolle's theorem says is that if I have some function that looks like this is the slide I had up the other day. If I have some function that looks like this, if I can say that f of a, there's b, if I can say that that f of a is equal to f of b, and this is a big point, is that the function has to be differentiable on the interior of the interval AB, in other words, in the open interval AB, then there must be some point in the interval where the tangent line is horizontal. It sort of makes sense because assuming the function is if the function is a constant, then its derivative is going to be 0 every place. So it's always going to have a horizontal tangent. If the function's not a constant, then it must go up or down at the beginning. And if it goes up, so let's take the example that I've drawn here where it goes upward. What that means is that it must have had a positive derivative here. So this is going to be slope is greater than 0. And the slope can't just be greater than 0 forever, or else the function would just keep going up and up and up. So at some point, there must be a point where the slope is less than 0. So it can go, so at some point the slope must be less than 0. And therefore, if it started out greater than 0 and ends up being less than 0, then it must have actually passed through 0 at some point. So that's exactly what you see right here. See, there's a question, can I give a problem that you would see that includes Rolle's theorem? Yes, I can. Actually, we did one. Didn't we do this example the other day? Barely. Okay. Why don't we just do it again in that case? No, that's not what I meant to do. Okay, wait a minute. Okay, here we go. So let's do this example. Okay, so let's do this example again. Let's just go through it again. So, all right. So this is an example. Verify that Rolle's theorem is satisfied for f of x sine x on this interval. So let's just draw the function we're talking about. So that's the sine function. Y, this is x, there's 0, pi, that's 2 pi, that's 3 pi, etc. Okay. So what we're interested in is the interval, I call that pi over 4. And here we have 3 pi over 4. So that's the interval pi over 4 to 3 pi over 4. Okay. So we want to do is first verify that Rolle's theorem is actually satisfied. In other words, recall that what Rolle's theorem says is, Rolle's theorem says that we need we need for f of a and f of b to be equal to each other. And we need the function to be continuous on the closed interval, differentiable on the open interval. So in the problem, it's given that a is equal to pi over 4 and b is equal to 3 pi over 4. How do we know that? Because that's the interval. Okay. So first of all, f of x is equal to sine x. And that means that f of a equal to f of pi over 4 equals the sine of pi over 4 equals root 2 over 2, right? And f of b equal to f of 3 pi over 4, which equals the sine of 3 pi over 4, which also equals root 2 over 2. So we have the condition fa equals fb is satisfied. All right, everyone with me so far? Everyone understand why you need to verify that in order to see that? Yeah, okay, good. In order to see that Rolle's theorem applies, because where was this? Up for a minute. Oh, that's right, because I don't have Rolle's theorem up here. Okay. So Rolle's theorem requires that FA and FB are equal to each other. Next thing we need to do, all right, so that's condition 1. Next thing we need to do is F continuous on AB. All right, so is it? What do you remember about continuity? What's the rule for continuity of trig functions? The answer here is yes, because sine x is continuous where defined. That's the rule for trig functions. Trig functions are always continuous where they're defined. And sine is, of course, just defined every place, so that's not really an issue. Next is f differentiable on the open interval AB. And answer to that is also yes. Fairly easy to show because we have f prime of x equals cosine x, which exists for all real numbers x. Okay, so these are the conditions that you have to show for Rolle's theorem to apply. We have to show that FA equals FB, that F is continuous on the closed interval AB. Let me just make it clear that that's closed. And differentiable on the open interval AB. So we have Rolle's theorem is satisfied. In other words, the hypotheses are satisfied. Recall that every theorem is if hypothesis, then conclusion. So what we're asking, we say, is a theorem satisfied, is we're asking, is the hypothesis true? The hypothesis here is a compound statement. It's the compound statement that, where was it? Sorry. It's the compound statement that F is continuous on the closed interval AB, differentiable on the open interval AB, and FA equals FB. So all of those conditions are satisfied. And we can then conclude that therefore there is C in the interval AB such that f prime of C equals 0. Okay, so where is f prime of c? Now, where is this number c? Well, it's very easy to find because we already found here that f prime of x is equal to cosine x. So what we're looking for is we want to find values c such that cosine c equals 0 and c is in the interior of the interval. Okay, well, we already know what the cosine function looks like. Sort of running out of space to draw it, but this is y equals sine x. So y equals cosine x looks like this. See, that's 2 pi, that's 0. We know that this is pi over 2, and this is 3 pi over 2. We're interested in the interval 3 pi over 4. I think of a better way to draw it. This is the interval pi over 4 to 3 pi over 4. It just kind of straddles pi over 2. So we can see that this is the place where the cosine function is equal to 0. So the solution to this is going to be c equals pi over 2. So this is the number c whose existence is guaranteed by Rolle's theorem. Rolle's theorem says that as long as conditions 1, 2, and 3 are met, there's going to be some number c such that f prime of c equals 0. We, in fact, found that number c. Sorry, I'm just waiting for a comment. Would we need to sketch the graph, or can we just set cosine equal to 0 solve? No, you can absolutely just set cosine equal to 0 and solve. I just find most people are sort of they relate more to the trig functions if I draw them. That's the only reason I drew it. But certainly all of this works whether you actually can sketch the graph or not. And in many cases you can't. The idea is you want to at least understand an example where you can visualize it so that you can see why it works in situations where you can't. Okay. All right. So let me. There's this now. Okay, so what I want to do is we're now beginning section 4.3. And that takes us to a theorem called the mean value theorem, which is actually just kind of an extension of Rolle's theorem. So the picture for the mean value theorem is this, and then I'll let me just draw the picture, and then I'll explain it in the context of I'll explain what the actual words mean. So if I have, say, some function like this, so this is y equals f of x, as you know, it's an arbitrary calculus function. If I draw a secant line here, color a little different. If I draw this secant line, so this point here is a f of a, and this point is b f of b, just because that's always how you would draw a point. And that's always what the coordinates of a point are going to be if you have a function. So what the mean value theorem says is that as long as the function is continuous on the closed interval AB and differentiable on the open interval AB, then there must be some point here where the tangent line is parallel to the secant line connecting the two endpoints. So that's really what we have here. So notice that we have conditions that are very similar to what we said for Rolle's theorem. Assume that f is continuous on the closed interval AB, differentiable on the open interval AB. There exists at least one value c in the interval AB such that f prime of c equals that expression that you see there. Well, think about what this is. The slope of this line, m, is going to equal the rise over the run, so y2 minus y1 over x2 minus x1. But if you look at what we actually have here, this is y2, and this here is y1. So that's going to be fb minus fa over b minus a. So what it's saying is this, if the slope of the secant line is described by this is the slope of secant line connecting endpoints, then that means there must be some point in the interval where the tangent line is parallel to the secant line. And in fact, we can even draw that and give it a name. Let's see. So as you can see, this is really a generalization of Rolle's theorem. That, Rolle's theorem is really the specific case where if FA is this, so if FA equals FB, then F of B minus F of A over B minus A just equals 0. In other words, the tangent would be horizontal. So Rolle's theorem you can think of as just a special case of the mean value theorem. The reason that we teach it this way is that actually Rolle's theorem was proved first. The mean value theorem is proved as an extension of Rolle's theorem. If you have the mean value theorem, you don't really need Rolle's theorem at all. But this is the more general version of this. And as you can see, just like with Rolle's theorem, if I allow for a possibility, like let's say, trying to think, a good example of that would be A, B. Allow for the possibility that, let's say, function can turn a corner. In other words, not differentiable. And here I've got m equals 1, m equals, let's say, -1. The secant line looks like it has about m equals 1/2. I'm just making up these numbers. I'm just trying to show how if you don't have this condition that the function is differentiable on the entire interval AB, then you can't really, this doesn't necessarily hold true. It's the fact that a differentiable function is very smooth, so it turns gently and it's going to acquire all the different possible slopes from one endpoint to another. Makes this work. So, all right. So what type of problem would we see here with the mean value theorem? Okay, so let's verify that the function f of x equals root x satisfies the MVT on the interval 1, 9, and find the value c whose existence is guaranteed by the MVT. All right, so we know what the three conditions are that we need for the mean value theorem. We have to have f is continuous on closed AB, differentiable on open AB. Actually, that's it. Those are the two conditions that you need for the mean value theorem. So let f of x equal root x, which it does. So 1, say f of x is continuous on 1, 9. We know that that's true because powers of x are continuous where they're defined. 2, f prime of x equals 1 over 2 root x. It's one of those things, I've said it a couple of times, but that's just one of the derivatives you sort of want to commit to memory, is that the derivative of root x, of square root of x, is 1 over 2 root x. So this exists for all x in interval 1, 9. So we have the two conditions for the mean value theorem. And then we say 3, actually it's not a condition so much, so we say therefore there is value c in 1, 9 such that f prime of c is equal to square root of 9 minus the square root of 1 over 9 minus 1. This is, of course, going to equal 3 minus 1 over 9 minus 1, which is 2 over 8, or 1/4. So there must be some place in the interval where the slope of the tangent line is 1/4. Let's draw what we're talking about here. Here's f of x equals root x, like this. That's roughly 1. That's 9. So the claim is that there must be some place where the slope of the tangent line is 1/4. That's going to actually be right about here. That's just a picture. That doesn't demonstrate anything. What we have to do is actually solve for it. So we can find c. So we know that f prime of x equals 1 over 2 root x. So what we're trying to do is solve the equation f prime of c equals 1/4. So that means that 1 over 2 root c equals 1/4. So that gives us 4, just doing like cross products here. You can solve for this however you want. 4 equals 2 root c. So divide by 2, get 2 equals root c, and that gives us c equals 4. So this is the value for where that happens. Okay. Everyone got that? Any questions about that? I'm just waiting for the comments. Yes. Yes. So, okay. So the question is, could there be a scenario where the graph is not differentiable at one of the endpoints? the fact is we almost never care about differentiability at the endpoints. Like, consider the following. Let's suppose that I had defined the function in the following way. F of x equals 10 for x less than 1, root x for 1 less than or equal to x less than or equal to 9, and 10 for x greater than 9. Then what you'd have is a function that looks like this. That's 1, that's 9. Here's going to be, up here you have 10. So in this case, for the reasons that I discussed the other day, the function is not differentiable at 1 and 9. Why? Because it's not continuous at 1 and 9, and a function has to be continuous in order to be differentiable. But if you notice, nothing about this in any way affects the conclusion that if I draw this secant line here, which has a slope of 1/4, there must still be some point here where the tangent line is parallel to it. That's not in any way affected by what's going on at the endpoints of the interval. So you never really have to check for differentiability at the endpoints for the simple reason, I'll just back up for a minute. The theorem doesn't require it. The theorem only requires that it only requires continuity on the closed interval, and says that for differentiability, you can exclude the endpoints. So what the theorem is saying is it doesn't make any difference what's happening at the endpoints as far as whether the derivative exists. The only requirement is that the function be continuous at the endpoints. Answer the question? Okay, good. All right. So, all right, so we now get to the next topic. Is, here we go. Okay. So increasing and decreasing functions. If you recall, there's actually there was actually a definition of increasing. Say that f is increasing on the interval I if for all x1 and neater, all x1 and x2 in I, whenever x1 is less than x2, follows that f of x1 is less than f of x2. This is the algebraic definition of what it means for a function to be increasing. If you notice, I haven't used any calculus whatsoever in that definition. All I've done is talk about functions. What this means is that if I want to know if, let's say, this function is increasing on, say, this interval, this is the interval I. You can think of it as AB, but it doesn't matter. We're just calling it I. What that means is that if I pick any pair of points, x1 and x2, it's certainly the case that in this diagram, x1 is less than x2. We know that because if you look at where x1 is, it's to the left of x2. And it's also the case that this is f of x1, and this is f of x2. So you can see that f of x1 is in fact less than f of x2. I've picked two specific points, x1 and x2 in here, but it doesn't really matter. You can see from the way I've drawn the function that if I pick any pair of points, x1 and x2, as long as they satisfy this condition that x1 is to the left of x2, it will be the case that f of x1 is below f of x2. That's the algebraic definition of increasing. We're now finally at the point where we can switch to the calculus definition of increasing. And this is something, for some reason, our book doesn't call it this. It calls it the sign of the derivative theorem, but its more common name is the monotone function theorem. And what the theorem says is that if f is a differentiable function on the open interval ab, if f prime is greater than 0, in other words, if f prime is positive, then f is increasing on ab. If f prime is negative, then f is decreasing on ab. Well, what's the picture here is if I have ab, if I draw this function, it looks like this. So notice that no matter where I am on the function, I can pick basically any point here. There's a tangent line. There's a tangent line. There's a tangent line. No matter what point I pick on this interval, if I draw the tangent line, I always get one with a positive slope. So here you can see that m is greater than 0, m is greater than 0, m is greater than 0. All of these tangent lines have slopes greater than 0, and the function, in fact, is increasing. In other words, it's rising as you go as you proceed from the left to the right. And of course, we can do the same thing with decreasing. You can say that if I have this function here that's decreasing like this, A, that's B, any tangent line that I draw in the interval AB, there's that one, there's that one, there's that one. All of these have negative slopes. So this is the characteristic now of an increasing or decreasing function, is that we can say the function is increasing or decreasing on an interval based on whether its derivative is positive or negative. And that's going to make it a lot easier than applying the algebraic definition. Question about that. What if there's a slope equal to 0 in that interval? Very, very good question. I was actually just about to get to that. Pat yourself on the back. So let's suppose I have a function that looks like this. A little bit more pronounced. So let's say that that's A and that's B. So the question is, if I assume that at this point here, I assume that at f prime of c equals 0. So there's one point in the interval where the slope is 0, but otherwise you can see that here I have f prime is positive, and here I'm also going to have f prime is positive. It's clearly greater than 0, and the only issue is what's going on at c. So question is, which of these intervals is the function increasing? So on which of these intervals is the function actually increasing? Trying to figure out how the pull feature works. A to C, C to B. Okay, So we got a couple of answers. This is getting interesting. Oh, I'm sorry. And sorry, answer that again. This is what I meant to write. Okay. Anyway, I'll just give you the answer. It's kind of interesting to watch people, but unfortunately, there's a lot of confusion between capital and lowercase letters. The correct answer is all of them. And yeah, so okay, so Christian asks, isn't it still increasing at point C? And the answer is yes, it is. So if you think about what happens, let's suppose that I say that C is x1 and some point here is x2. It's still clearly the case. Here is f of x1 and here's f of x2. So even with the point 0, it's still the function still meets the algebraic definition of even with the point where the slope is 0, the function still meets the algebraic definition of increasing, even though you can't tell through the monotone function theorem that it is increasing at that point. So you do have a couple of corner cases where the function flattens out for just a single point and then starts going back up again. If that's the only thing that happens, if there's only one point here where it becomes, in other words, if it's not 0 for an entire interval, but just for a single point, then if there's a single point of 0 in between two positive derivatives, then we would say the function is increasing on the entire interval. Fortunately, this is not something you even need to really worry about, because if you look at it, the way the monotone function theorem is stated, it says that if f is greater than 0 for all x in AB, then f is increasing on AB. That doesn't exclude the possibility that f is equal to 0 at one point in the interval, but it's still increasing. It just says that if you can say this, then the function is increasing. That doesn't mean that it might not be increasing under some other circumstances. Okay. So let's see. Oh, sorry. There's a term I have to give you to understand this. The term is monotone or monotonic. So we say that function monotone, or sometimes we write the word monotonic on an interval I if it is either increasing or decreasing on I. So monotonic is just sort of one of these, terms that collects the two opposite terms. So let me show you in general what this means. So what I'd say is that I have this function here. Let's just make it really easy. Y equals x squared. What we'd say is that, let's call it f of x squared. So we'd say that f is increasing on 0 infinity f is decreasing on negative infinity 0, we would say that f is monotone on negative infinity 0 and on 0 infinity, because these are both intervals where the function can be said to be entirely increasing or entirely decreasing. So monotone is just sort of the collective term that refers to both of those, and that's why we call the theorem above the monotone function theorem. Let's wait for Andrew's question. With a sine graph, would we say that the function is monotone in multiple parts? Yes, that's certainly true. So here we have the sine function like that. Oops. So what we'd say is if this is f of x equals sine x, and keep in mind where those points are, this is pi over 2, 3 pi over 2, 5 pi over 2, etc. We would say that it's increasing on negative pi over 2 to pi over 2, 3 pi over 2, 5 pi over 2, etc. Because you can kind of see, I didn't draw this part of it, but you can see where the slope is positive. We'd write it that it's decreasing on pi over 2 to 3 pi over 2, then 5 pi over 2 to 7 pi over 2, etc. Then, sorry, I have to go over here. You'd say it's monotone on negative pi over 2 to pi over 2, pi over 2 to 3 pi over 2, etc. Because I could just collect all of those intervals together, say that it's monotone on all of them, even though it's not the same kind of monotone. On some of them it's increasing and some of them it's decreasing, but those are still the places where it's monotone. Makes sense, I hope. Okay, good. So, all right. So here's the kind of question that we can answer. Let's find the intervals on which this function is monotone. Let's find the intervals on which f of x equals x squared minus 2x minus 3 is monotone. So we know that we're going to find those through the derivative. Just a second. Sorry, my computer is just acting weird for a minute. I should fix it. Okay. So all right, so we have f prime of x equal to 2x minus 2. So what we're solving for is increasing where 2x minus 2 is greater than 0, decreasing where 2x minus 2 is less than 0. So all we really have to do is solve the inequality. And say 2x minus 2 is greater than 0 gives us 2x is greater than 2, or x is greater than 1. And you should be able to see that 2x minus 2 is less than 0 is just going to be 2x is less than 2, or x is less than 1. So we can say that this function is increasing on increasing on 1 infinity, decreasing on negative infinity 1. So it's monotone on negative infinity comma 1 and on 1 infinity. So that answers the question. It's monotone on those two separate intervals. Notice that 1 itself is not actually part of that interval, and shouldn't be hard to see why. This is obviously a quadratic function, and what it's going to look like, I forget exactly whether it's above or below the x-axis, but it doesn't really matter. The point is that its vertex is at 1, so it's going to be a parabola that looks like this, and you can see it's certainly not monotone on the entire, it's certainly not monotone on negative infinity to infinity, because it changes from decreasing to increasing on that interval. What we're building up to here is the idea that you can use derivatives to figure out a lot about the shape of a graph. And that's going to be important in a number of different ways. But the first thing we've seen is that positive or negative derivatives tell us whether the graph is falling or rising, whether it's decreasing or increasing. So, all right. So let's see. So let's see one particular way in which this can actually be used. And that's going to be the first derivative test. This is, a couple of you had asked the other day what the connection is between finding that a point is critical and knowing whether it is a local min or max. Recall that Fermat's theorem tells us that local mins and maxes can only occur at critical points, but it doesn't tell us whether a particular critical point is a min or a max. So the first way that we can determine that, it's not the easiest way, but it is one way we can determine it, is something called the first derivative test, which will tell us whether a critical point is a local min, a local max, or possibly neither. So the first derivative test says, let C be a critical point of f. If f prime changes from positive to negative at C, then f is a local maximum. And if f prime changes from negative to positive at C, then f is a local minimum. So what does this really say? What this really says is, if I were climbing a mountain, here's a point. I'm going to tell you that this is a critical point. Is that the peak or valley of a mountain? I wish I had that poll feature now. Good, everyone's stumped because you can't tell. Because I haven't drawn anything else in. If I draw it like this, then you can clearly see that it's the peak of a mountain. On the other hand, if I had taken the same point, and drawn it like this, in both cases, it's still a critical point. But in this case, it's the valley. The only way you can tell is by looking at what's around it to the left and right. So here we have is, I'll write it actually in calculus notation. We have an increasing function to the left and a decreasing function to the right. And in the case of the valley, what we have is we have a decreasing function to the left and an increasing function to the right. So this is the telltale sign of whether a particular critical point is a min or max, is based on what it's doing to the left and right of that point, which we can now tell through the derivative of the point. So this is the formal statement is that if f prime changes from positive to negative, here we have positive, and when I say that, I'm assuming that we're proceeding in the direction from left to right. Start at positive and go negative, then this is going to be a max On the other hand, if we start negative and go positive, then this is going to be a min. So this is how you can tell whether a particular critical number gives you a local min or a local max. And the name for this is the first derivative test. That's what, fortunately, our textbook doesn't change the terminology. That's essentially what every textbook that I'm aware of calls this. Okay. So any questions about that concept? Okay, good. Is everyone alive? Everyone's been very quiet. No. Okay, everyone's dead. Here we go. Thanks. Okay. Okay, so analyze the critical points of f. All right, so here we have a function f of x. I'm not even going to draw it because the whole point is that we should be able to do this without drawing it, just based entirely on the principles that we've covered. So f prime of x, we need a derivative in order to analyze what the critical points are. So f prime of x is equal to 3x squared minus 27. All right, so what we want to do is we want to find critical points, critical numbers. All right, so we can clearly see that there are no critical numbers that involve the derivative not existing, because the derivative function f of 3x squared minus 27 clearly exists every place. So that's not going to be an issue. What we want to do is solve f prime of x equals 0. It gives us 3x squared minus 27 equals 0, where 3x squared minus 9 equals 0. That gives us x equals plus or minus 3. So critical numbers are 3 and negative 3. So, all right, so first of all, could, let's say, x equals 1 be a local max? No. Why not? Correct. Not a critical number. It has absolutely no possibility of being a local max or local min. Good. So these are the only points we'd have to look at to find the mins and maxes. So what we want to do now is figure out what is a min and what is a max. So let's look at x equals 3. What we want to do is figure out is the derivative positive or negative to the left and to the right. So what we want to do is choose point to the left and a point to the right. Choose 0 to the left, 3, and 4 to the right, 3. Okay. Now, why can I choose these points? The answer is that I'm choosing, let me draw this. We know that the critical points are negative 3 and 3. So what I know is that let's suppose that I'm not saying which one it is, but let's suppose that the derivative is positive here. Well, if the derivative is positive at, let's say, x equals 2, then it also has to be positive at x equals 0. Why? Because let's suppose that the derivative was positive at 2 and negative at 0. Well, then it must have crossed 0 somewhere around there. But that can't be, because if it did, then f prime would have had another critical number, and we know that it only has this number, and this number is critical. So we know that the derivative never changes to 0 between two critical points. It's going to stay, so it has to stay the same sign, SIGN, between critical points. So I can pick any number that's convenient as long as I haven't crossed over another critical point. So the ones that I'm going to pick are, that's critical point 1, that's critical point 2. Just for simplicity, because it's really easy to evaluate at 0, I'm going to pick 0, and then I'll pick 4. So prime of 0, that's going to be 3 times 0 squared minus 27, which equals negative 27. And f prime of 4 is going to equal 3 times 4 squared minus 27. So that's going to be 48 minus 27, which is 21. So, as it turns out, when I was writing was wrong. Here I have negative, and here I have positive. So I have a function. So at 3, what I have is the situation that the derivative is negative, and then it starts going up like that. So we conclude that x equals 3 is the location of a local min. Okay. Everyone with me so far? Good. So now, just with the remaining space that I have, let's do x equals negative 3. Again, I already have f of 0. I'm going to choose x equals 0 and x equals negative 4. So we already know that f prime of 0 is equal to negative 27, and f prime of negative 4, it's actually going to come out exactly the same. It's going to be 3 times negative 4 squared minus 27 equals 21. So here we actually have negative 4. We're going to have positive. So now, this point, negative 3, we've got a positive derivative. It's going up and up and up and up like that. And then down here, it goes to negative. So we would say that x equals negative 3 is location of a local max. Up these notes, but these are the two answers. We've just analyzed the critical points and found that they are, in fact, a local min and a local max based on first derivative test. All right. Everyone clear? Okay. Let's see. I just want to skip ahead a little bit to make sure that I have time to cover this idea. Oh, actually, yeah. Let me just point something out. It's possible to get a critical point that is not either, why the negative number is the max. Let me just go back. I just want to answer that question. So, oh, okay. So you're saying why is it that -3 is the max and +3 is the min? That's because I want to get another piece of paper here to answer that. So the question is, why is it that -3, why is this the max and this is the min, when clearly -3 is less than +3? The answer is because what I'm looking at are y values. What this graph looks like, if I were to draw it, is something like that. So I'm not looking for whether the x value, one particular x value, is less than another. It's clear that this is a max and this is a min. This is what this first derivative test is actually saying. It's even though it's certainly the case that -3 is less than 3. Does that answer the question? Okay, good. All right. I just want to show you an example of where the where a critical point is not either a min or max. So here, if f of x equals x cubed, clearly the derivative is 3x squared. So if I find critical points, critical numbers, clearly there's no place where this doesn't exist. We're just solving 3x squared equals 0, which implies that x equals 0. So let's pretend that I don't know anything about what this function looks like, and hopefully some of you at least do know what the function of x cubed looks like. I can pick arbitrary points on either side. I'm going to pick 1 and -1. Choose x equals -1 and x equals 1. Those are the points on either side of the critical number that I'm going to check. So f prime of -1 equals 3 times -1 squared, which is 3, and f prime of 1 equal to 3 times 1 squared, which is also 3. So here, on the left side, I have positive, and on the right side, I also have positive. So what I conclude that x equals 0 is neither min nor max. Now, what does this function actually look like? This is x cubed. Looks like this. So as you can see, it flattens out just for an instant at x equals 0, but then keeps going up and up and up. It's not like it rounds out on top and then starts going the other way. It just flattens out and then keeps going the way that it was going. So it's possible to get a critical number that's neither a local min nor a local max. You still have to check those, but recall that the first derivative test says if f changes from positive to negative, or f changes from negative to positive, we can say it's a local min or a local max. If it doesn't change at all, then nothing happened. We can't conclude either one of them. Oh, is it only where you're dealing with odd functions? No, I've just happened to have drawn a really symmetric function. Second. I mean, consider this. F of x equals x minus 1 cubed. In other words, just the cubic function shifted by 1. So that's neither odd nor even. And it has the same issue. All right, I want to go on to get to the last few concepts. Okay. I can hang around for a few minutes after class if anybody has any questions. We've talked about the idea that a function is increasing or decreasing, but there's another way of looking at the shape of a graph, which is if I have two functions that look like this, what we would say is that this function is what's called concave up, and this one is concave down. And it really just has to do with the question of, if you view the function as a bowl or a smile or a frown, which way it's going. The thing is that there's actually a way to understand this in terms of derivatives. Take a look at the concave up function. First, just ponder this for a minute. It's not possible to say that the concave up function is increasing or decreasing because it's actually both. It depends on where we are on the function. Clearly, it's got this smile. Sorry. Clearly, this function has this sort of smile or bowl up kind of a shape, regardless of whether I'm in this part of the function where it's decreasing or this part where it's increasing. This is not just another way of saying increasing or decreasing, but we can describe it in terms of derivatives in this way. Notice that here I've got a tangent line which is like m equals -10, and then here I have a tangent line which is like m equals -1, and then here I have a tangent line that's like m equals 0. Here, once again, I have m equals 1, and then up here, I've got a tangent line of m equals 10. So if you look at these tangent lines that I've drawn, slope goes from -10 to 1 to 0 to 1 to 10. And I'm just making up these numbers. So what can we say about the slope of a concave up function? Well, it certainly looks like the slope of its tangent is increasing. And similarly here, I've got m equals 10, and then it's going to be m equals 1, m equals 0. So here I go from 10 to 1 to 0 to -1 to -10 on a tangent line that has a very strongly negative slope there. So we say is that this is sort of the way of characterizing these sort of up and down functions, is that a function is concave up if its slope is increasing from negative, is increasing, it goes from low to high, and it's concave down if it goes from high to low, so if it's decreasing. So here we have is the slope is increasing. Here we have the slope is decreasing. So how do we detect if the slope is increasing? In other words, since the slope is given by f prime of x, we can say the slope is increasing if the derivative is positive. And here we can say the slope is decreasing if the derivative of the derivative, sorry, in both cases, I mean the derivative of the derivative is negative. But I can write this, of course, as f prime prime of x is positive and f prime prime of x is negative. So what this is now another feature of a graph that you can detect through the derivatives, but this is through the second derivative. We say that a function is concave up if its second derivative, we can discover that a function is concave up if its second derivative is positive, and is concave down if its second derivative is negative. So I was looking for the question. Quadratics always have a constant concavity. That is correct, in fact, yes. So, all right, so this is the formal definition of concavity, is that f is concave up if f prime is increasing on AB, f is concave down if f prime is decreasing on AB. In other words, or if f prime prime is greater than 0, or f prime prime is less than 0. That's how we detect concavity through the derivatives. Now, last concept I just want to give is the second derivative test. This is the other way to detect whether a critical number is a local max or a min. Take a look at what happens if this is a max. Let me draw that function again when we analyzed. So if you look at it here, it certainly looks like at this point, concave down. At this point, it's concave up. So if these are C1 and C2, we ought to be able to detect whether they are a max or min, whether they're a max or a min, depending on whether the function is concave up or concave down at the critical number. Notice, by the way, now, is this function concave up or concave down? Well, it certainly looks concave up there, and it certainly looks concave down there. So that means there must be some point where it switches from concave up to concave down, which I'm going to put about there. And there's actually a name for this called an inflection point. So this is the basic machinery of how you use the second derivative. I had hoped to get all the way up to finding, to using the second derivative test to find whether something's a local min or max, but I'm out of time. So we'll start with that when we return on Monday. Okay. If anyone has any questions, I can stick around for a few minutes, and I got to turn everyone's microphone on to make it easier. Oh, question about, you mean the derivative quiz? Yes, there's just some bookkeeping that I have to do on that, and I will post those. Okay. Local min and max don't occur. Do the critical points have to equal the same number, or just both be positive and negative? I'm not sure I understood the question. Anybody who wants to stick around, I can stay around for like 10 minutes. So I'm just going to turn the recording off now and say goodbye. And anybody who would like to stay, I'll just turn your microphone on. You can ask questions.